Okay. So this is the 10th seminar in the series that we are organizing with Giray and Karen. This time we have Ruben Minasian. We are happy to have a talk on a subject that probably interests many people, and there is a critical mass, so we can start already. So, by the way, Ruben, you can tell whether people can interrupt you during the talk or maybe...
More better.
Okay, so yeah, it's good to have more interactive seminar. So thank you, Ruben, for giving this talk, and maybe you can take over.
All right, so thank you. And well, I guess I should start from apologies for the idiotic title. This title and the talk contains no moral judgments. So think of low and high as, I don't know, energy scales or anything else. But once more, it's just a pun. Okay. All right. So here is a plan, and the rough motto of this talk would be, it's written, what you want to or must know about supergravity, but do not want to ask string theory. Okay. Once more, there is no moral judgment here. So there is a reason you don't want to ask string theory or string theorist. I mean, there is a saying that if you ask carpenter what the moon is made of, the answer will be wood. So if you ask string theorist what kind of supergravity should look like, they will tell you what they can construct. And what you want to do is to actually ask questions about what is consistent. And doesn't matter where it comes from. Now, of course, this question is asked mostly by string theorists. The answer is kind of win-win. Meaning, if somehow we show that the only things in supergravity which are consistent can be obtained from string theory, it's good for us. If we find things which are consistent and we cannot do them, maybe it's also kind of a good excuse to learn how to do them, or actually see that we indeed cannot do it. Now, what's the main thing you need to know about supergravity? And yes, I would have liked to, I don't know my audience, and right now I don't see it because I shrunk the list of participants. So I would have liked to be able to say with a straight face that you don't need to know any string theory and I will not be using it. I am almost not lying, but okay, I cannot be sure that I can control my language and the jargon and all that. So please, again, stop, ask, explain yourself if you feel like you can explain it for the audience better than I do. All right, so what do you need to know? Main thing about pretty much any supergravity that you can pick at random is that as it stands, it is inconsistent. And what I mean by as it stands, as let's say you read about some kind of two-derivative action where people have shown how the algebra closes, the thing is supersymmetric and supersymmetry transformation are given, and all that, okay? That theory will be inconsistent. So, and there are different ways of dealing with it. First is somehow restrictions. So, I mean, supergravity will tell you that, oh, we can couple this amount of supergravity with, I don't know, in this given dimension with this many supercharges to this and this matter multiplets. So a typical thing which happens is you restrict the matter. Somehow it can be possible that coupling 5 matter multiplets works, but coupling 10 does not. After you do your sort of rough restricting, you also have to add more stuff. So as it stands, this theory is going to be incomplete. Finally, you will need to probably do things which we normally don't do in supergravity in order to kind of restrict the consistency conditions a little further. Okay, so the first part of the talk, I'll just give you examples of all this. Some of them are just absolutely banal. Everyone knows them, or everyone sort of in some domain knows them. Some are obscure and not very well studied, and I may say also wrong things. I do apologize to people present and absent. There are no credits, no attributions on the slides. So, but if ask me if you want some result. So in some ways, the main tool for this first part will be kind of anomalies. So I'll be talking a lot about anomalies just to avoid any confusions when I call what I call an anomaly is a top form. So in a D dimension, an anomaly for me will be a top form. Some of you might be used to hot star of it. Okay. And another thing you sort of know is that, okay, the anomalies typically can be descended from some kind of characteristic classes. So I will be using these things kind of interchangeably. So sometimes I will be showing a D+2 form polynomial and I will still call it an anomaly. Okay, but the idea is that yes, anomaly can be derived from it by descent. So this is the first part of the talk, and in the second part, I will go kind of beyond anomalies and talk about something a bit more specific, about some bounds in 6-dimensional theories, and this will be a recent work with my student Peng Cheng and Stefan Tyson. Okay. So let's start. Okay, I mean, everyone, again, I suppose, knows that supergravity theories appear in low energy limits in string theory. One of the first big string results was showing how vanishing of Walsh-Schmidt beta function gives you equations of motion of supergravity. And supergravity in that case was actually kind of what we call an S sector, or the basic 1-0 gravity multiplet. Okay, so let me start from it. So in the minimal amount of supersymmetry that you can have in 10 dimensions would be 16, and there are 2 multiplets, and the gravity multiplet contains graviton, an antisymmetric 2-form, a dilaton, a scalar, bosonically, and the fermions. And the fermions are chiral, so you can check and compute the anomaly, and you will see that the answer is non-zero. And there is no way of fixing this, okay? There is another, however, anomalous multiplet with the same amount of supersymmetry, which is Yang-Mills, which contains fermions and vector fields. And then, again, I mean, this is, of course, you can do these things from string theory, but just from purely point of view of supergravity, you can say, okay, can I sort of add up different anomalous pieces and obtain something which is anomaly free? The answer is no, it's never possible, but there is the second best scenario. So what you can do is, once more, we are talking about anomaly in 10 dimensions. So as I said, there will be a 12-form polynomial. So if you manage to factorize this 12-form polynomial in a form like this, so a 4-form, wedge and 8-form, then you can somehow devise an anomaly cancellation mechanism. So what does this mechanism involve? It involves a coupling of a B field, which is this 28 here, to the 8-form part of this polynomial. And it also involves assigning some kind of funny transformations of the B field. So what you would be saying is that this B field should not be invariant, neither under diffeomorphisms nor under gauge transformations. So this guy has to be sensitive to those transformations. In other words, when you construct the 3-form out of it, you will want to construct a gauge invariant or diffeomorphism invariant 3-form. So it will not be just dB, but it will be dB plus extra stuff. And you will get this kind of anomalous Bianchi identity. And the 4-form here is just a 4-form which appears in this polynomial. And then what you can say is, look, this term, which is called Green-Schwarz coupling, it will not be invariant under diffeomorphisms and gauge transformations, but its failure to be invariant will exactly be equal to the anomaly I have. So in other words, I have an anomaly cancellation. So the theory is anomalous, but I also have an anomalous coupling to cancel. Okay. Now, here is the first place already where you encounter a problem, kind of dichotomy between string theory and supergravity. So if you do this exercise in supergravity, you find 4 anomaly-free possibilities. E8 times E8, SO32, the things in sort of color, but also E8 times U1 to the power 486 or U1 to the power 496. Once more, for those you don't know, you can easily see that all of these have dimension 496. The reason is simple. If you look at anomaly polynomial, it will contain a piece like trace R to the 6, a 12 form, with the coefficient, which is given by dimension of the group minus 496. So you want the dimension to be 496 as the first, the crudest condition to be able to factorize this anomaly in this form. So you want to get rid of irreducible pieces. Okay, now I will not tell you how to show that these 2 theories in black, which do allow for anomaly-free supergravity, are inconsistent, but they are. And the 2 others are realized in string theory. Okay, so these 2, I mean, the technology which is involved in is not very dissimilar from the one which I will be showing in the second part of the talk. Okay, now another way of kind of dealing with these anomalies is adding more stuff, which in practice in this case means adding more supersymmetry. And there are 2 ways. Yes.
Can I ask a question? So there are many more possibilities with this dimension of the group. So why only this 4?
No, there aren't. I mean, if you write the anomaly polynomial, these are the 4 groups which will allow you to write the anomaly in this form.
But there is more condition than just the dimension.
Of course, no. I mean, you need to kill the irreducible part of the gauge part, trace f to the 6. Then you will have to be able. I mean, not every combination of r squares and f squares and f to the 4s and r to the 4s can be factorized. So when you are through with it, you will find these 4 possibilities.
So it's either simple or abelian kind of structure.
They are written. Okay, now when you add more supersymmetry, you have 2 possibilities. Either, I mean, essentially you are adding 2 supercharges with 2 spinors with 16 components. They are of the same chirality or different. Okay, when the theory is chiral, so no chirality, no problem. In the case when it is chiral, naively you would be making things worse. Okay, you are definitely doubling the existing anomaly. You see your existing fermions, kind of, there are 2 of them now. But also you are adding this guy, which is a self-dual 5-form or 5-form field strength, and somehow magically you get a full identical Z. So it's an anomaly-free theory. Okay. So here is already first illustration of the points, which at least the first 2 points that I was started from, that yes, I mean, you construct some supergravities, you will have to necessarily make some restrictions in some cases. For example, choose the gauge groups, and you will need also to add fix. You need to add couplings in order to make theory consistent. Okay. Now let's do a thing which we can do. Let's look at other dimensions. So if I want to go to 9 dimensions, I can do it 2 ways, right? Again, I can look at what supergravity tells me, or I can just take my 10-dimensional theory, presumably consistent one, and put it on a circle. again, I don't know my audience, so I wanted to explain, at least very sort of sketchily, appearance of kind of symmetry groups upon this compactification. So let's look at the simplest object, some three-form H, which necessarily exists in 10 dimensions. And now I am assuming that everything has an isometry. So my space-time is a U1 vibration, and Lie derivative of the generator of this isometry annihilates H, which means I can, okay, I'm dropping pullback signs. I can write H as in this form, okay? And then let me take the simplest case when the H actually is 0, H is closed. You can see that closure of this equation in 10 dimensions, in 9-dimensional language, actually will break into two different equations. So a piece which roughly contains E, a piece which contains the, the direction around the circle, and a piece which doesn't. And the piece which doesn't, you see, the H3, it's no longer closed, and it's dH3 equals H2 wedge T, which I can just write as F plus square minus F minus square. So you see a 1-1 metric appearing somehow here. And if I did it on two circles, I will get O2, and so on, okay? If you look at what supergravity tells you, it tells you that in 9 dimensions, the theory should have a symmetry, which is SO1, n. And at supergravity level, this is over integers, over reals, okay? So there are two ways of reading this. One is by addition. You say, oh, it's a theory with n plus 1 vectors. So there is one vector, this one, which lives in gravity multiplet. So the difference between minimal gravity multiplet in 10 dimensions and in 9 dimensions at the level of bosonic fields would be extra vector. And if I did it in 8 dimensions, there will be extra 2 vectors. Okay, and I have n vectors in vector multiplets. You can also, by multiplication, say, oh, this is the number of scalars in the n vector multiplets. So in this case, I have n vector multiplets with one real scalar each. Okay, and these things have a parameter space or a moduli space, which is kind of a useful concept. Okay, now, if I was naive and I started from my 10-dimensional string theory, I would have said, look, I take the theories which I have. I sort of told you there are two of them, E6 times E8 times E8 and SO32. And I can compactify, I can turn on different Wilson lines. Maybe I will break some of the gauge group, maybe I will not. But there was a piece which had rank 16. And then I added one more guy, you know, this F minus. So I would have n equals 17. Supergravity tells me you can do any n. I mean, what supergravity teaches you is how to couple Young-Mills to gravity. Okay. So here is a place where you can start worrying about kind of consistency conditions. So first consistency condition actually comes from the paper of Wheaton and Alvarez-Gomez, when they talk about not local gravitational anomalies, but global. So these are transformations, these are associated with transformations which cannot be continuously related to identity, but at infinity, they tend to be one. And okay, it's also a feature of theories in 8K and 8K plus 1 dimensions, so 8 and 9 dimensions, that these guys do not like odd number of Majorana fermions. I mean, the mass matrix would contain 0, so it's not a good, these are not good theories. So that essentially tells you immediately that, oh, n has to be odd. So 17 is good, all right? But still, any odd number can be 351. Now, there were some other arguments which kind of would bound this, but the latest we have comes with the kind of the third point of I would trying to make here, kind of global surprises, okay? That that parity can act as an internal symmetry. So in other words, you can consider your theory on non-orientable manifolds, in particular PR2. And you demand that it is consistent. So the theory, a consistent theory, should be consistent on all backgrounds in which you can put it. Okay, and again, I'm not explaining this. This is going to be purely declarative, but that considerations lead to restricting n to values 1, 9, and 17. Actually, 9 can be obtained from the 10-dimensional theories which I told you about. Both theories, I mean, okay, E8 times E8, it's easier to see. It has an obvious Z2 outer automorphism. So when you reduce this theory on a circle, you turn on Z2 holomorphism. So that roughly identifies two E8s, puts them at level 2, but ends up giving you a theory with rank 9. Okay, it's harder to see, and I will not explain how to get the other case. But in all these three cases, which are allowed by sort of current considerations or considerations of consistency, all these are realized as string theories. Okay. So this is kind of okay. At this point, I somehow illustrated already all the things I wanted to say. So you restrict, you add things, but you can also consider sort of exotic backgrounds or backgrounds which normally you wouldn't be considering in supergravity, and this also give you sort of constraints. All right, now let me do another thing. I will consider theory with 32 supercharges, and I will consider this theory in 8 dimensions. I will start with the claim that this theory, in order to be consistent, requires the following coupling. So it's an 8-dimensional theory. It has a coupling which contains an 8-form polynomial in curvatures. So it's a combination of trace r to the 4 and trace r square. And it's multiplied by a function of a complex scalar, which has funny kind of automorphic properties. So this guy is actually not invariant under SL2Z. Okay. Why I am adding this term? Why is it required for consistency? Because it has an anomaly to cancel. So let me explain it very briefly. So if I look at this 8-dimensional theory with maximal supersymmetry, the moduli space is given by SL2 times SL3. Again, perturbatively, as I just explained, any theory which has a 2 torus and comes from 10 dimensions should have O22. And O22 is a product of 2 SL2s. So at least by now, you should all immediately see the SL2 times SL2 part. One of the SL2s becomes SL3 because it's non-perturbative. Okay. The function I'm interested in, this scalar, is okay. Let me do it in type 2A language. It's given by the B field, which is kind of has 2 components along the torus and the volume of the torus. Okay. I mean, as a supergravity, this is maximal supergravity. So there I don't have much freedom. All the maximal supergravities come from toroidal compactification of maximal supergravities in 10. Okay, so here I am not losing any generality by talking about reducing the theory. Okay. All right. Now, when we talk about the cosets, so there is a numerator and there is a denominator. Numerator, there is only discrete part of this numerator which survives as a full symmetry. Otherwise, okay, in supergravity we would call it a U-duality group. And once more, it's some discrete part of it is an exact symmetry. The denominator is a gauge symmetry. Fermions coupled to it. Okay. Now, what we do in practice, I was just talking about complex scalar. You can do the calculation in your head that the coset is 3-dimensional actually. So you are somehow gauge fixing. Now, what happens is when you gauge fix the coset, you lose the gauge symmetry, the U1 symmetry in this case, but the discrete part of the denominator ends up being nonlinearly realized. And in particular, if you had U1 anomalies, you would have SL2Z anomalies now. Okay, now, why do you have U1 anomalies, or do you have U1 anomalies? The answer is yes. You don't have to do much, you just have to look at supergravity. Okay, here I wrote for you, and this comes from the supergravity literature. Just look at the variations of the fermions. Actually, you could look, there was one reason I put these things. If you look at 10-dimensional type 2B theory, these things in red are the U1 charge assignments. Okay, so in 8 dimensions too, I have the theory with this U1 gauge symmetry, everything is carrying a U1 charge. Okay, but if you look closer, there is also this gamma 9. And there is another thing that, okay, you have a 3 form which somehow splits into a pair of dual 3 forms. Okay, but you track your U1 charges, you use your standard anomaly formula, and you end up computing the polynomial of this form. So F is the field strength of this composite connection, and X8 is the guy which I wrote here. Okay, I see something in the chat. Okay, sorry, this wasn't a question. Okay, so I have somehow a U1 anomaly in 8 dimensions, and as I said, once I gauge fix, and normally we would be working with the gauge fix theory, the U1 anomaly disappears. There is only SL2Z anomaly, but and it can be fixed by this contour type. Okay, and okay, I have written also this X8 for you, this particular polynomial, which appears from just reading off these respective polynomials. You take all these polynomials from Alvarez, Gomez, and Witten, you sum them up. This, of course, it has to be some combination of P1 square and P2, or trace R square square and trace R to the 4. It's this particular one, okay? No problem, I can fix this anomaly, but you may kind of pause and say, look, it's somehow it's strange. We start from a good type 2A or 2B theory, anomaly free in 10 dimensions. We do something which is very, very innocent. We just put it on a torus. Why all of a sudden we see something new? Where does this new anomaly come from? Something must have been present already in 10 dimensions. Another thing is here. The reason I wrote it in type 2A language is this U is the internal component of B. So if I make my torus very large, I send the volume to infinity. Okay, I will lose this part of the modulus, but instead of 8-dimensional B field, I will have 10-dimensional B field. And in some ways, you can see what this coupling will survive this decompactification, and it will become B2 wedge X8. Instead of 8 form, now it's a 10 form. Okay, but it's there. Moreover, it's even there in 11 dimensions. So in 11 dimensions, the theory, okay, I go now to, well, there will be C3X8. Okay, before I go to 11 dimensions, I cannot resist, I will make some comments about this particular combination, this X8. Somehow this guy seems to have, okay, so here is the first manifestation of it. I just wrote some anomalies for individual fields, spin 3/2, spin 1/2, and self-dual 4 form in 8 dimensions with different U1 charge assignments. That's what the answer is. Okay. Now I'll tell you a couple more ways of realizing this exactly same X8. One, probably most kind of invariant or abstract one, actually this is the way how string theory sees this object, is the following. Consider 8-dimensional Euler density. Here, I have written it for you. It's an 8 form, 4 powers in curvature, and the tangent space indices are contracted by epsilon. Okay, so here is an Euler density. Now let me do something. I write this Euler density in spinor representation. So in other words, instead of r's, I write some kind of r heads, where instead of tangent space indices, I'm using SO8 triac. Okay, I use spinorial indices. And so I have 4 gamma 2s here. And then you can show that this chi hat, this spinorial Euler density, actually, you see, Hopf theorem tells us that it's a condition of nowhere, existence of nowhere vanishing vectors is vanishing of Euler number. So if you want to answer a question about nowhere vanishing spinors in 8 dimensions, you would do this calculation and demand that this chi hat equals 0. Okay. But anyway, if you write this chi hat in this form, and then you just write it in normal language, in other words, you do some gamma matrix algebra and simplify the expressions, what you see is that this chi hat is related to ordinary chi, the real Euler density, plus something which is proportional to X8 polynomial. Now, I just told you that this X8 polynomial actually in some form should lift to 11 dimensions. Okay? And now I will tell you just completely another way of finding the same combination. So here is 11-dimensional supergravity. It looks extremely simple in terms of bosonic fields. So it has a graviton and the 3-form field. And so, okay, here is the Hilbert-Einstein term, is the kinetic term, and then the only kind of interesting part is this Chern-Simons coupling of the form CGG. It's a top form, 11 top form, okay? So this is the supergravity. Now, one thing I will kind of, what the super Poincare algebras do, they have super extensions. And if you look at the extensions, you can see what kind of BPS objects, what kind of solitons are allowed. Okay, but you can also see it just simply from seeing what kind of fields you have. So let me try to dream up a source for this field. So instead of normally in supergravity, I would say G4 equals DC3, DG4 equals 0. Now, if I have a source, I will write some kind of source equation. Since I started from a 4 form, its source will be given by a 5 form. So this 5 form delta is, okay, it's some kind of generalization of ordinary delta function, except it's a form. So what does it say? That if I construct an 11 form, which contains this delta 5 in it, and I do integration, it will put me on a 6-dimensional complement of this 5 form delta. Okay, it's a Poincare dual of some 6 cycle. And by standard nomenclature, the branes, the objects whose extension is 6-dimensional, are called 5 branes. So string has 2 dimensions, membrane has 3, and so on. Okay. So 5 brane is a very funny theory. If you do the zero mode analysis, notice this is all, you can do all of this at the level of supergravity. Actually, in 11 dimensions, you don't have strings anyway. I could do things in 10 dimensions and leave them to 11, but all I'm saying here is at the level of supergravity. I'm just looking at classical solitons. Once I found the soliton, I can do the zero mode expansion and check what lives on that soliton. And what lives on that soliton is a 6-dimensional chiral multiplet with 16 supercharges. So the theory has 32, the soliton has half, So 16 supercharges. So the field content of this tensor multiplet is a self-dual tensor field, 5 scalars, which parameterize these 5 transverse directions, transverse to the kind of 5 brane, and 4 fermions, which are in representations of SO5. So the R symmetry group of this multiplet is SO5, which is also again, corresponds to geometric 5 dimensions transverse to the brane. Again, from absolutely standard considerations, and the fermions are chiral. Okay, so you see the multiplet is chiral, it contains chiral fields. So in gravitational backgrounds, when it's coupled to gravity, there will be gravitational anomalies. I can just compute them. Again, going back to the same paper by Alvarez, Gomez, and Witten, I read off what the anomalies are. And the fermions are non-trivial under the SO5, which is the structure group of the normal bundle. They live in representation 4. But for the moment, let me forget about it. Let me just look at trivial normal bundles and just consider gravitational anomalies. So I have one self-dual field and 4 fermions. I add them up, and that's completely different way of seeing this X8. It's exactly the same 8 form as I was showing you before. Okay. Now, the purpose of this exercise was not to just find another way of rewriting this simple-looking combination of 2-point reagents, or P1 square and P2, but actually motivate why this term was already present in 11 dimensions, and it is really related to anomalies. So you see, I have a theory, 11-dimensional supergravity, has no chirality, has no anomalies, seems like perfectly good classical theory. And then all of a sudden I say, oh, this theory has solitons. And if these solitons are there, somehow they are anomalies. So we don't like this idea. So what we would want to do is to say, oh, let the theory be consistent together with its solitons. So the soliton is chiral, is anomalous. The theory is not. What can I do? I can try to devise a coupling which, in absence of this soliton, is completely legitimate, meaning it has all the symmetries it should have. In this case, it would be diffeomorphism and the shift of the C field by a closed 3-form. So I need to respect this in absence of this brane. But I can also say, oh, when the brane is present, I want this coupling to somehow become anomalous. Okay? And the anomaly to be such that it is restricted to the brane itself so that it can cancel the brane anomaly. Okay, you can check that coupling of the form C3 wedge X8 actually does the job. Okay, if I integrate by parts and write it as G4 and I vary with respect to diffeomorphisms, and I again integrate by parts, I will hit the delta function or the delta form. At the end of the day, I will get something, oops, which gives me a 6-dimensional anomaly. So if I, you see, I was doing it from the bulk. The only purpose of it was to, so I'm devising, I'm putting a polynomial which would be canceling the 5-brane anomaly polynomial. Okay, so that's X8. Of course, if you were in type 2A string theory, you could compute this, and you can, and it's done. And of course, these arguments agree. But it's also exactly the same X8, which I showed you appearing in 8 dimensions. Okay, so one way or another, I mean, even if you think that you are in theory with maximal amount of supersymmetry and the theory is not anomalous, and all that, somehow it's a little more subtle. The theory is still not complete without some higher derivative couplings. which would cancel the anomalies. Okay, in one case, it was a metamorphosis, transformation of an anomaly. Okay. In 8 dimensions, this looked like an SL2Z anomaly. In 11 dimensions, it looks like 5-brane anomaly. Well, actually, I mean, in 8 dimensions, you can also think of it as 5 branes. But okay, so of course, string theory is more than supergravity plus any number of higher derivative terms. I mean, it does have effects which are also non-perturbative both in string coupling and in string length, but okay, I'm kind of staying away from this. Okay, let me show you another thing and do exactly the same, but in theory with 16 supercharges. So I had shown you this group SO2, N already. Okay, there I called it big N plus 1. Okay, but this is there. And again, the concept, the important thing that you need to keep here is, again, there is a U1. Okay, so there is still going to be a composite U1 which couples to the fermions in a chiral fashion. So in other words, there is still going to be an SL2Z anomaly. And I can just compute it in the same way for arbitrary gauge group G, okay? And I'm devising this function. Okay, in this case, I will be just considering theories. Okay, I need to have N equals 18, let's say, in the simplest case. And I will just look at U1 squared times some G, which is rank 16. So I have two complex scalars, which I call in summary with Z's and Z bars, and I can devise some automorphic function object. I mean, of course, it's symmetric under these two. Okay, here I call them U and T. Okay, I can compute the anomaly. I can write a counter term. Now I can also ask, okay, what about string theory calculation? And here is a funny thing, is what you find is that your supergravity answer agrees with string theory answer only when this G is equal to SO32 or E8 times E8. But in reality, I have many more consistent theories. So even if I just do string theory, I start from 10 dimensions and I put it on T2, I can have lots of G's because I have lots of different Wilson lines. And I mean, the calculation have been done for simpler cases like SO16 square or SO8 to the 4 as written here. So anytime there is a Wilson line, these two calculations disagree. So schematically, the answer always looks like this, okay? There is always a part which you can sort of obtain from naive reduction of 10-dimensional Young-Mills field. There is a part which looks like this anomaly, or let's say naive SL2Z anomaly that you would compute. And then there is a part which is sensitive to the massive Wilson line contributions, okay, or whatever, vector multiplet contributions. Now, if I am a supergravity person, so okay, string theoretically, let's say I understand this. Now, what do I do from point of view of supergravity? First of all, I can say, look, finding any counter term is good. I'm given a theory. I can see that it has SL2Z anomalies. I don't need any massive sector in order to write a counter term. But from other side, I can do also something else. I can say, oh, look, let me add massive sector and let me integrate it out. If I do that, that will change the counter term. So in particular, I can find massive contributions such that it matches the string result. So very naively, I would have an infinite number of massive completions of this 8-dimensional supergravity, for all of which I can cancel this SL2Z anomaly. Now, can this be right? Are there really this infinity of theories. If I put these theories on sort of nice backgrounds like tori and stuff, I don't see anything new. Instead, I can try to put them on sort of a little bit more complicated things. Manifolds with positive C1. Okay, so they are curved. So, okay, I did not write, there are a bunch of global constraints here. And when I satisfy these global constraints, effectively, what I am doing, I mean, you can see that what you are doing is some kind of geometric construction, whereby you are constructing a torus bundle over this manifold with C1, positive C1, in such a way that this C1 is cancelled. Okay. And the thing is that this torus can degenerate. So things which were normally massive actually become massless at those points. Put it differently, if depending on the massive completion, and the thing is that if I do this, if I put the theory on, in the simplest case, on a P1, I can preserve supersymmetry. I start with theory with 16 supercharges. This way I obtain 6-dimensional theory with 8 supercharges. This theory is necessarily chiral, has 1-0 supersymmetry, and generally anomalous. And if, for example, I do not include any massive states, I will obtain an anomalous 1-0 theory. Now, I don't have a theorem. I have just simply checked it in few cases that, oh, if you turn on massive style or complete the theory with massive sector, as instructed from 10-dimensional string theory and the choice of Wilson lines, let's say, in order to go to SOH to the 4, you obtain 6-dimensional theory, which is anomaly free. And if you do not, you don't. But I don't know this thing in general. And I don't know anything about sort of general 8-dimensional theories, which do not contain 2U1s or contain more or are more complicated or less complicated. Okay. But here is another illustration of how the supergravity is kind of inconsistent because it is incomplete. So in this particular case, seemingly again, simple supergravity with a lot of supercharges in nice dimension like 8. There are no anomalies normally, I mean, no chiral anomalies. Actually requires a subtle completion by, so is incomplete without massive states. And the way you are adding massive states seems to be kind of very much prescribed. Okay. And once more, here notice I had to put it on theory on a space with positive C1. Actually, the next complicated case, I would put it not on CP1, but I would put it on real 4-dimensional manifold with positive C1, a Kähler one. These are mostly non-spin manifolds. So you can preserve supersymmetry on a manifold which does not admit spinors. Okay. The answer is kind of given. I already gave it to you. There is this composite connection, and the manifolds are complex and they are spin C. And this composite connection has funny quantization properties. Altogether, the theory, I have spin C spin or spin C objects, and that's good enough to define supersymmetry. Just like previously, I already mentioned non-orientable manifolds. So you see, sometimes to kind of check these consistency conditions, you are doing things with supergravity, or you are putting it on backgrounds, which you normally would not be doing within supergravity. But one way or another, sort of we are learning things. And as I said, in principle, all of this, I mean, with sufficient calculational power, can be done without invoking, without knowing anything about string theory. Okay. But you restrict the field very, very much. I mean, okay, you are throwing away infinite number of theories because you could start with any gauge group, any rank, infinite number of them. Okay. And these kind of considerations, which so far have been mostly related to anomalies, I mean, the ones that I showed explicitly, seem to be already very much restricting the fields to just a few, okay? All right, now I think I will go to the second part of the talk, and I will do it kind of very, very fast. Okay, I spoke longer than I thought. And sort of, I will just show you some cartoons. So the second part of the talk is about 6-dimensional theories with minimal amount of supersymmetry. So 1-0 supersymmetry is just the point where I stopped previously. So here are all the representations that we have. There is a gravity, a tensor multiplet, Young-Mills and hypermultiplets. So the fields in red are bosonic fields, which are chiral and anomalous. So I have tensor fields which are self-dual, one tensor field which is self-dual in gravity multiplet, possibly many tensor fields which are anti-self-dual in tensor multiplets, and then I have all sorts of chiral fermions. And once more, just like in 10 dimensions, I can have anomaly cancellation. So I can never get a strict 0, but I can get an anomaly cancellation if I have some kind of factorization. So index alpha runs over all the tensor fields. So it's from 0 to a number of tensors. And sort of this object omega is a symmetric inner product on the space of tensors and has a signature 1, n. These x's are the same because sort of self-duality. That the equations of motion and Bianchi identities for these tensor fields are of course related because the fields themselves are related by self-duality constraints. So if I am given a theory, if I tune my matter correctly, I can read off this anomaly polynomial. If I read off this anomaly polynomial, you see I have a Green-Schwarz coupling, which means I can explicitly, okay, I will show you, here is how these x's look like. It's trace r square with some coefficient and trace f squares for all the gauge groups with some other coefficients. And you see these coefficients are absolutely completely fixed by the matter content. Because the matter content tells me what the anomaly polynomial is, the anomaly polynomial tells me what these couplings are. Okay? So here is the situation. We have many ways of realizing these theories. I mean, I just mentioned you one just 2 minutes ago, how to put 8-dimensional theories on manifolds with C1. Positive C1, morally, this is equivalent to heterotic string on K3. There are perturbative 2B constructions, all sorts of orientifolds. So we have lots of models, okay? But it's very finite, the number. Now, we have also one sort of particular class, and I would like to talk about it, which is F theory. So we have a class, large class of 1-0 theories which are obtained from F theory. Now, I assume some people in this audience do not know about F theory. I'll just give you a working definition of what F theory is. I apologize to those who do. It will not be adequate. It is believed that lots of theories in 5 dimensions with 8 supercharges can be obtained, or maybe all, by compactifying the 11-dimensional M theory, 11-dimensional supergravity, which I showed you, on a Calabi-Yau threefold. So Calabi-Yau manifolds are Kähler manifolds with vanishing C1, with trivial canonical class. They are Ricci flat. They have covariantly constant spins. So they preserve supersymmetry. This is nicest geometry you can think of. Okay. So generic, consistent, good 5-dimensional supergravity is obtained from Calabi-Yau compactification of 11-dimensional supergravity. If I take 6-dimensional theory with 1-0 supersymmetry, the theories that I am considering now, and I put them on a circle, I would obtain 5-dimensional supergravity with 8 supercharges. So it's arrow which goes one way, but not all 5-dimensional supergravities with 8 supercharges can be lifted to 6 dimensions. Not all of them. So by reducing 6-dimensional theories, I obtain only a subclass of 5-dimensional theories. Okay. And what is this subclass? This is the subclass which corresponds to compactifications on elliptically fibered Calabi-Yaus, not on generic Calabi-Yaus, but on elliptically fibered. Okay. And okay, so in other words, if I have an elliptically fibered Calabi-Yau and I put my theory, M theory, 11-dimensional supergravity on it, that theory can be decompactified, can be lifted to 6 dimensions. So this is what I am calling F theory. But you see, it's very, very much attached to this condition of elliptically fibered Calabi-Yau. Okay, now, so F theories, okay. One nice thing about it is that they are sort of, everything is geometric. And notably, these anomaly cancellation conditions, or the conditions for factorization of the polynomial and everything, they all appear as geometric conditions. Okay, very good. But the property that I'm really interested in this talk is that all of these manifolds, or all F theory models, have a bound on them. Okay? It's not a very strict bound, it's not a very hard bound to satisfy, but it's a bound. And this bound is, I showed you these coefficients, A's and B's and stuff. And this bound tells me that there is some combination of this coupling or these constants in the theory, which has to satisfy some relation. Okay? And that condition is perfectly geometric. This is the Kodaira condition for elliptic Calabi-Yaus. So if Calabi-Yau is perfectly smooth, what I do is, I think of it as a base, which is given by a Kähler manifold with positive C1, and a torus bundle, elliptic bundle, which degenerates. The base has positive C1, the Calabi-Yau has C1 equals 0. So if I cancel this C1 by this extra contribution, and the manifold is smooth, this is the simplest form of Kodaira condition. In general, I can have singularities, so there will be another, I will show you the condition a little later, okay? So that provides me with the bound. So the picture, and the question is, okay, can I join all the consistent 6-dimensional theories by some bound, and not just F theoretic ones? See, right now, what we know is if you give me a theory, it's a consistent 6-dimensional theory, I can try to check whether this bound is satisfied or not. If it is satisfied, then it's quite likely that the theory has an F theoretic realization. If it's not, it's not. It doesn't tell me that the theory is inconsistent. So if we look at all 6-dimensional theories, Karapet, I have been speaking for an hour now. So what should I do?
We started a bit late, and you can go on. So yeah, okay. Maybe 5-10 minutes to wrap up, okay. And then we will discuss. So,
if I look at all 6-dimensional theories, I can see a picture which is like this. So there is an infinity of 6-dimensional minimal supergravities. Mostly they are anomalous, so obviously inconsistent. Even if I restrict myself to theories which are anomaly free, there is still infinity of them. So in particular, you see, for example, there are families, infinite families of this type. It showed that if I have a number of tensors, which is given by 9 plus 8k, and I have gauge group, which is E8 to the power k, k can go to infinity, all these models are anomaly free. Of course, this is very, okay, any string theorist knows we will never get an infinite. I mean, we can get large ranks by putting, say, heterotic string on very singular k3s and with small instantons, etc., you can get creative about it, but you are never going to have infinity. Okay, so a question is, are these models, are models like this consistent, or, I mean, are we really kind of missing some mechanism in string theory which tells us, oh, we can crank up the rank of the gauge group to infinity, or it's actually just deficiency of supergravity? So one way or another, there is infinity of anomaly free theories. And there is a finite number of F theory models. And notice that I have put a strict boundary around them. And that's what's supposed to be the sort of this Kodaira bound, okay? So that they all satisfy some numerical conditions. And then there are some other consistent theories, okay? Either they are obtained by some string constructions that I mentioned or not, but they are consistent. There is clearly some overlap because of dualities. So we know there are lots of models which can be obtained both in F theory and heterotic, and they are dual. Okay, so this is the rough picture. And what I want to do is I want to make this picture kind of prettier. Okay, and the way I do it is the following. So I have this theory with this anomaly polynomial, and what I do, I add sources to it. So the logic is very much to what I showed you in 11 dimensions. There I had a 5 brane. Here, my sources. I mean, you can do the similar numerology that if I start from dh and I want to add a delta function to it, it will be a 3 form. No, sorry, 4 form, which means the object which is charged under this is has a Volt volume extension 2. It's a string. Don't confuse it with string of string theory. This is string which is just classical solid. Okay. And what I would want is that these strings are consistent. That supergravity without strings is consistent, supergravity with strings is consistent, everything should be consistent, okay? Now, first thing is that if I analyze these strings, they are chiral. So there is a 4-0 theory there. So in other words, once more, I should have a mechanism like I described in 11 dimensions, some kind of inflow. So I cannot just put in any string. It's better that the field content of this string is somehow such that the anomalies can be canceled by inflow. And if I do that, okay, that's sufficient for me to actually, okay, sorry, I will not be showing you any details, but it's sufficient for me to read off the central charges. Okay, so here they are. There is a piece which is linear in charge, and there is a piece which is quadratic. From other side, I have a gauge theory. I mean, there are gauge fields, and these gauge fields couple to the string. So there is another kind of natural central charge, which is just induced by the current algebra. Okay, and it's given like this. And what I would want is the unitarity of the string. In order for this string to be unitary, I would want that the central charges, which are given by anomaly cancellation, which really count the physical number of bosons and fermions on the string, is equal or bigger than the current algebra, the central charge. Otherwise, the theory cannot be unitary. Now, there is a conjectural moment in here, which is the following. So first I have to sort of narrow down I have to impose the physical constraints on charges. Okay, like to have well-defined moduli space and things like that. But the other, you see, right-hand side of this expression is quadratic in Q. So you can just look at it and say, oh, look, if you make Q very large, I mean, here, the field content is fixed. So you make Q large enough, the right-hand side will be always bigger than the left-hand side. So what's the problem? So the conjecture is the so-called completeness conjecture, which says that no, I mean, we cannot, if the charge is allowed, there should be a consistent state with that charge. So we cannot just by hand say, oh, we don't like sort of small charges. We just will choose solitons with big charges. Okay. So this, once one believes this conjecture, okay, one can just simply use this as a criterion to restrict these six-dimensional fields. Okay, and this has been done, and it does eliminate a lot of theories. It does eliminate this infinite series that I showed you. So in principle, all is good. So the reason I am giving this talk is that you can kind of make it a little bit more geometric, and you can write it. Okay, you can say, well, what it has to do with Kodaira condition. Okay, and okay, I'm skipping through a lot, and I'm showing you another bound, which is obtained from the exactly same objects by just reducing them to 5 dimensions and looking at them from 5-dimensional point of view. And the bound, which they are very close. I mean, if you take a particular model and you analyze them, they are very, very similar. It's essentially a rewriting. And the rewriting is in this form. And the thing which kind of made us jump is this minus 12 in front of Q times A. As strange as it is, you know, because otherwise the formula look fairly familiar and similar. So what about this magic 12? So this is where Kodaira comes in. Okay, so here is the Kodaira condition, or actually this. So it says that I have a canonical divisor, which is multiplied by this magical 12, which has to be kind of a residual divisor and sum of all the singular divisors. Okay, so if there are no singular divisors, if the Calabi-Yau is smooth, I just have a cancellation. And this is just a condition that, I mean, either way, it's a condition that I have a Calabi-Yau, that I have a manifold with C1 equals 0. It's a question simply how I cancel it. Okay, how do I cancel this C1, which is given by minus 12k here? And Kodaira condition says that its intersection with any Neff divisor should be effective. So in other words, this intersection is semi-positive. Okay, now having obtained the 12 in our bound, it makes it kind of direct, and I can translate, or it has been done, a series of nice papers by other people, that these Kodaira conditions can be translated into conditions for these physical couplings, A's and B's. Okay, I can do my comparison in any language I like, but the bottom line is, again, because of this appearance of 12A, I can directly compare kind of, these two conditions. And once more, let me skip through pretty much everything, and okay, arrive to conclusions, or just tell you the conclusions, that in vast majority of cases, this unitarity condition on the BPS string that we obtain is automatically satisfied whenever you have a positivity condition, whenever Kodaira is satisfied. So indeed, we were looking at a condition which is generally weaker than Kodaira, because we know that there are models, consistent string theory built models, which do not satisfy Kodaira. They fail Kodaira. So which means if there is a bound on them, this bound is weak. So generally, for most of the cases, anytime you have 3 gauge group factors, this bound is automatically satisfied every time you satisfy Kodaira. There are 3 particular cases where this bound is stronger than Kodaira. So it doesn't say that elliptically fiber Calabi-Yaos are inconsistent. What it says is that, okay, we might have situations where seemingly we have stronger condition than Kodaira, but simply there is no underlying Calabi-Yau, or that the divisors have more non-trivial numerical properties than generic ones. So in other words, there are some special Calabi-Yaus with special singularity structures where the divisors are somehow more interesting than we thought, or they satisfy kind of stricter conditions, okay? But altogether, everything can be put under the same equation, and the picture, the modified cartoon that we have is now of this time, that yes, we can bound all these consistent theories which satisfy this unitarity constraint by a kind of a single domain, which does contain F theory inside. And inside F theory, there possibly is another kind of domain, which is, you know, this kind of one where there are funny divisors with a stronger numerical constraints than we generically assume. And in some ways, there is a sense in which kind of you move from interior of the domain towards the exterior, which is simply how much closer you are to satisfying these constraints. So everything which is outside, and this is an infinite number of theories, is inconsistent, even if it does satisfy the anomaly cancellation, which so far has been kind of the most sure way of weeding out inconsistent supergravities. All right, so I think I can stop here, but hopefully you will believe me. I tell you that, okay, there is still a lot can be done about sort of trying to check different consistency criteria on different candidate theories for quantum gravities. And this is kind of an interesting and evolving story, but I will stop here. Thank you.
Thank you, Ruben. Maybe we can start with questions. You can unmute yourself and ask questions. We are not that many to raise hands. Maybe I can start with one question. So the discussion of conditions on consistency for supergravity was for T equals 6 mostly. Why is T equals 6 important?
All of them are important. I mean, you see, as I was showing in the beginning, sort of the closer you are to the kind of major canonical supergravities in 10 dimensions, less ambiguity you have. You see, in 10 dimensions, there were just essentially, okay, with the anomaly cancellations included, okay, with between 2A, 2B, and 4 different kind of 16 supercharged ones. Okay, you started with the list of candidates, which is 6, given by 6. You are down to 4. When you are in dimensions 8 and 9, you have kind of very, very strong bounds. And there, okay, I did not tell, I mean, there is still a lot of theories All I told you is about the rank given by some numbers, let's say 9 dimensions, that the rank of the Young-Mills sector can be 1, 9, and 17, but there are lots of non-abelian groups of this rank, semi-simple or simple or whatever, which can be realized. I did not mention any of this. But in higher dimensions, there is kind of, I mean, things are, okay, I don't want to say simpler, but better understood, okay? Starting 7, for example, I mean, so 6 dimensions is the first one where you also can have matter, or you can have 8 supercharges. So in 11, you can have only 32. In 10, 9, 8, 7, you can have 32 or 16. Starting from 6, you have new matter appearing. So things are just somehow completely out of control. Okay, they start already getting completely out of control. And yeah, of course, I have no idea what starts going to happen when you go to 4 dimensions and reduce supersymmetry even less. Okay, so these are still nice. They would be corresponding to 4-dimensional n equal 2 theories upon reduction. Okay.
The question of consistency is only at the level of anomalies, if I understand correctly.
Well, no, the point of the second half was exactly this, that even with anomaly cancellation, you have infinite number of theories and extra criteria, in this case, the unitarity of the BPS objects, actually allows to pick a finite set out of them.
But so at the level of supergravity, there is no discussion of renormalizability, right? You're just assuming that there is some completion,
No.
UV completion.
I mean, yes, of course, meaning there would have been a completely different approach to quantum gravity, it's just constructed. So again, the point is not to do it, it's just to find criteria that any theory, any consistent theory of quantum gravity should satisfy, and then try to narrow the list of candidates.
Yeah, one more question. So can you explain the title? I didn't completely connect it with the content of the talk.
Supergravity is supposed to be low energy limit of string theory. So the rest was supposed to be just, I don't know, I didn't want to give a technical title. So.
Okay. Any questions?
Hello, can you hear me?
Yes.
Can you hear me? Yes.
Yeah.
So I have a question. Ruben, at some point you mentioned that some of the inconsistencies only became clear when you put them, when you evaluate the theories on some specific backgrounds, some more exotic backgrounds. So what's the criteria to know, which kinds of backgrounds? How far should we go? How exotic should we?
Yeah, that's a good question. I mean, you see, this is the place where it's kind of hard. I can pretend that I don't know string theory, but to some extent. So in this case, let's say choice of manifolds with positive C1 was kind of easy in the sense that, okay, I know I can put a heterotic string on K3. So when I am thinking of 8-dimensional theory with the same number of supercharges, I know that kind of a la F-theory constructions that, oh, I can put my 8-dimensional theory on CP1, and so CP1 should be a good admissible base. So I did not come up with something terribly imaginative, but I would say that, okay, look, if you have a background on which you can satisfy, you can preserve supersymmetry locally at least. Okay, this is a one to try. Of course, you know very well that when you are analyzing supersymmetry and trying to see where you can preserve supersymmetry, you will never be too exotic. You will start by assuming some kind of G structures and things like that. You would assume invariant spinors. While when I was talking about some kind of more exotic possibilities, there are non-orientable, non-spin, and things like that. So that where your local supersymmetry globally is essentially does not even require existence of spinors, at least.
So should there be like any background where you can potentially formulate a string theory?
Yes.
That should be, but we
Yeah,
don't know
I mean,
what
again,
the backgrounds are.
unless if you don't have a particular reason to exclude it, I think then it should be okay.
Okay, thanks.
Yara, you wanted to ask a question?
Oh, yeah, sure. So maybe similar to your second question, I haven't quite understood what, maybe I should, but I haven't quite understood what consistency means. So maybe I'll give two examples. So in these 8 or 9 dimensional cases, you told us that the supergravity should be formulatable on something which is non-orientable in order to be consistent. But later you said, well, it's okay to impose it at spin C, if I understood correctly.
No, these are two different cases.
Oh, they're two different cases, but I mean, but why do you need to impose? Well, okay. Anyway, that's one example, and then I'll say the other one. And the other one is when you were talking about M theory, and then also in the second part of the talk, you said that the BPS objects should be unitary in the theory. And so, yeah, so in the first example, yeah, I didn't understand why you imposed that the theory should be consistent on something which isn't orientable. I mean, I would say that consistent means that if you start with that there's some subset of configurations which you declare are the configurations of the theory, and when you evolve them, it stays in that subset. I mean, that would have been my definition of consistent. But I don't see how that gets you out of orientableness.
Fried and Hopkins showed that M theory on non-orientable manifolds is anomaly free. So, I mean, if the theory, right, if M theory does not have anomalies on non-orientable manifolds.
Sure, but why do you impose that the supergravity should be well defined on an orientable manifold, on the 8 or 9 dimensional supergravity?
Okay, let me say things in a different way. If I do, then I will get conditions. Now, if you have a good reason to sort of exclude PR2 from admissible backgrounds, then you will not buy this argument.
Okay, and similarly in the case, so which was most of the talk, I guess, of BPS objects. I mean, why, if you find that some BPS charge corresponds to something which is non-unitary, why couldn't you just say, so that charge doesn't exist in the theory? I mean, why do you have to change the theory?
No. That's why you have to verify. No, first you verify that, let's say, you have to impose conditions on charges, which are, again, good moduli spaces, positive tensions, all that. Now, if you can realize the charge, and for that charge you find a non-unitary object, then you would say, oh, we have a trouble. So,
but if you choose,
I mean, without this completeness conjecture, I would have said once more, there are lots of things which work only for large charges. So why not say that this is one of them? Okay, and the completeness conjecture tells us that no, this is not, we are not allowed to do this. That we should, if the charge is allowed by sort of physical considerations, then there must be a state corresponding to it. So we cannot just exclude it. So, and sort of having unitary sources is not, you don't move the poles, kind of. So you want a good moduli space, fine, and then within it, I mean, I do understand that the arguments a little bit look like, oh, this is Yes, they give us the results that we wanted to have.
Right. So, okay, but you're saying it's just a conjecture that the charge is realized. So if you have the conjecture, then there is a consistency condition.
You do actually test it. Again, there are set of conditions you have to impose on charges. You have imposed them, then you find the charge, a very particular vector of charges. I mean, with the, you look at the papers, they are spelled down with all the numbers and everything. You find a case for which then you see that your string for zero theory is not unitar. Once you find one of those for any allowed charge, you throw away the entire theory.
Right, but why don't you just put that it should be unitary as one of the conditions for having a charge? I mean, I don't understand why you accept the charge and then you don't.
As I said, that was not the starting point. You see, the starting point, you are talking about supergravity, so you want it to be kind of okay. Physical conditions. Yeah, I don't know. I mean, I do understand the question. I don't have a very good answer.
Okay, thanks.
Hi, Ruben. I have a question, but it's more on a technical point, actually, at the beginning of your talk. It's something that I've always been confused about. It's this SL2 anomaly that can or cannot be there in supergravity or string theory, in particular in type 2b. So you said that, for instance, in type 2b supergravity, so let's say you're at two derivative level, you fix the U1 gauge, and you get a non-linearly realized action of the continuous SL2 transformations, SL2R, right? Then you will find that there is some generator of SL2 which is anomalous at one loop, I guess.
Yeah.
And now you're still in supergravity and you say, is what you're saying that you can add a counter term such that you restore
yes.
an SL2Z symmetry?
Yes.
Okay. But, and this is still in supergravity.
Yes.
But wouldn't you somehow expect that you would not be able to see some SL2Z symmetry until you actually go back to string theory, until you have added all the infinite power of massive states?
Okay, also good question, but yeah, how to say it? Since these anomalies are one way or another related to brains, maybe you say that okay, in a way that's already some kind of stringy effect. Okay, but the truth is, yes, I can formulate it completely in supergravity language. And by the way, to be supergravity is not anomalous. If you compute this in 2B, strictly in 2B supergravity,
with the two derivative action,
that's not a matter of derivatives. If you compute the polynomial, it will be a 12 form, not a 10 form. So the 10 form was of the type x8 wedge f. And if you compute it in 2B, it will be exactly same x8, wedge f, wedge f. F in supergravity is d tau bar. So f wedge f is 0. So strictly speaking, in 2B supergravity is anomaly free. When you allow for 7 branes, in other words, again, when you put your theory on manifolds with positive C1s, then you say, oh, F is not actually d tau bar, but it's the C1 of the space-time. C1 squared can be non-zero. Then, so in other words, yes, to be string theory has an SL2 anomaly. To be supergravity does not.
I understand what you mean with.
But in 8 dimensions,
more complicated background, but
in 8 dimensions, supergravity already is anomaly. Okay. You don't gauge fix it, you have just a simple U1 anomaly.
Doesn't have an
yeah. If you gauge fix the U1, you end up with SL2Z.
Is a symmetry that
Franz,
Franz, I don't hear you well.
Yeah, I have my hand on the microphone. I just wanted to make it, but SL2Z is a symmetry of 2B string theory. We agree on this. You're
Yes.
not saying this is anomalous. Okay.
Yes.
Okay. Okay, thank you.
Any more questions? Maybe I can stop the recording now and then we can continue discussing.